I just got three things to say. God bless our troops. God bless America. And gentlemen, start your
Unbelievable! McQueen is fading! McQueen is fading! Fading fast!
No. 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 No.
It's every turn. It's costing us, man. What can we do about it? Man, you guys better get this done by race day. Your jobs are for sure on the line.
We'll be alright. We can for sure solve it with physics. Yeah, we can't afford another crash like that. The drivers are going too fast around the turns, but they also can't go too slow around the turns because then we lose time against the opponents. I wonder if there's a way we can find the maximum speed to go around these turns.
Go.
Alright guys, to solve the maximum velocity around a turn, we can actually use pretty basic Physics 1 principles. Basically, all we need to know is that when a car is making a turn, like in this diagram, it is moving in a part of a circle. So this circle actually has a radius, which is given. Also, there's only three forces enacted on the car when it's taking a turn, and one is the normal force from the ground off the car, which is equal with no bank, and on flat ground, it's equal to mg. The only other force is in the horizontal direction, and that's the centrifugal force. And in this case, for a car going around at this turn, it's the static friction. And that is the reason why the car is accelerating towards the center of the circle. It's because there's a force in that direction. So since we know that there's a force in that direction, the net force is going to be equal to the centrifugal force. So we can use this equation for the centrifugal force, mv squared over r. And we can also use the equation for static friction, which is mu sub s times the normal force, and combine these two formulas into mu sub s, normal force for now, but since we know it's equal to mg, we can just substitute as mg, then equals v max squared over r. Cancel out the m's, we get mu sub sg equals v max squared over r, and then to solve for v max, we get the square root of mu sub s, which is the static friction coefficient between the tires in the road, times g, and then times the radius of the circle. Okay, now let's apply this to our real life scenario. For our F1 car with a static friction coefficient of 1.5 between its tires in the dry road, it's going around a turn with 50 meters of radius. So using those values, all we need to calculate the Vmax is 1.5 v sub s times g, which is 9.8, times 50 meters, which is the radius. This marker is kind of dying on me, but it's cool. So that will give us, in meters per second, approximately 27.1. So there we have it.
And then that's 60.6
Yep.
miles per hour.
Pretty good. Ah! Oh my.
Okay, so Finn gave us a decent starting point here, but it's still wrong. I think the reason it's wrong is because in the model we had was just oversimplified. It was just a point mass for the car and only one friction force.
And some tires lose traction first, so it causes different types of, spinning or, scenarios. And I'm gonna explain these scenarios. And okay, so basically, before I teach you guys understeer, I'll have to explain how like an F1 car really works. It's not like your typical four-wheel drive or your typical Nissan or Toyota. It's very different. The front tires are the only tires that are being steered, and the back tires are the only ones that are given power by the engine. So basically, the back tires have to follow the front tires in the direction that the front tires are being steered into. And basically the front tires are the only tires that push on the ground. So basically, yeah, in a regular car tire, the car moves the car moves because the tire pushes on the ground, and the ground pushes back on the car's tire. And what this does, it provides a centrifugal force needed to go around this corner or the right turn. Unfortunately, during this turn understeer, the front tires lose traction for whatever reason, and they slide. So when they slide, they lose grip. And when the tires lose grip, the front tires, they can't push on the ground anymore, which means there's no actual centrifugal force going in this direction. So there's no steering movement because the front tires have lost traction. So basically, understeer is when the front tires lose traction. In F1, it feels like you're still moving in a straight line, the same direction that you were right before the front tires lost grip, and it's very hard to get out of this. Okay, now that you know how an F1 car, the basics of how it works, we know that the rear tires are, they're only tires getting power from the engine, and the front tires are the only tires that are being steered. Oversteer now is when the rear tires lose grip. So the front tires are still, turning, so there's still centrifugal force inward. But when the rear tires lose grip, the F1 car can just spin outward, rotate outward due to the slipping of the rear tires, and the car can, if not controlled, the car can just do a complete 360.
So now I'm going to answer an implied question that I'm kind of hinting at. Why would the front or rear tires lose grip first?
Basically, this can be caused by increasing the throttle on the F1 car or braking. I'm going to talk about throttling first. So increasing the throttle can definitely cause understeer, because increasing the throttle can shift the mass, actually, the bulk of the mass, well, not the bulk, but the center mass, towards the back rear of the car due to inertia. And basically, this means that there's a larger normal force towards the rear of the car, where the rear tires are. And this means that there can actually be a larger static friction force toward the rear of the car on the rear tires. This means that, compared to the front tires, this means that the front tires can actually give out before the rear tires, which does understeer. Braking does not in fact cause understeer, but it can definitely cause oversteer. For example, braking leads to a load transfer similar to the one we just discussed, however it's the opposite. Now the load transfers to the front of the car because of inertia, like we discussed before, and now that it transfers to the front, there's more mass in the front temporarily, and this while it's braking, and this means that the front of the car does have more normal force, and more normal force means that the front tires do, or possibly can have a larger static friction force, meaning that now the rear tires could be the ones to give out first, causing oversteer. Now I'm going to explain something called aerodynamic downforce. So basically, you have to look at this airflow diagram. This looks like an upside down wing. Normally a wing needs a lift. This wing wants to provide the opposite of that. It wants down the opposite of lift. Wants to force downward. So basically, there are some classic theories that are not confirmed. One of the theories is that the correct theory is that yes, there's actually a low pressure zone under this upside down wing, a high pressure zone on this above this upside down wing. However, one of the reasons is that the air below is squeezed the tighter area, and because it squeezes the tighter area due to Bernoulli's principle, the velocity here is actually greater than the velocity on the top, and as we already know, low pressure, higher velocity is equal to lower pressure. Another explanation would be that you have to meet at the same time air, which has not been confirmed. This would mean that the velocity of times air because you travel greater distance because upside down wings the same amount of time. I cannot confirm any of these theories, so I have to think about it in basic terms. In basic terms, yes, there is a high pressure and low pressure zone, but you do not need to even consider this. Basically, as you can see from here, this wing is pushing the air up. So the wing is pushing the air up, which means there must be a third law pair reaction, and this means, I presume, that there must be a force on the wing downwards from the air. This means that now the free body diagram of the F1 car includes this down force, which means that there must be normal force up, so the normal force must increase, which means that in the car, think about the point mass this time, the tires must have more grip because the static friction force increases because the normal force increases. So this is why aerodynamic downforce can help us increase the grip. Yeah.
Alright, this was our old car right here. It didn't perform well enough because it didn't have this rear wing on the back here, as you can see. There's no little flap that catches air that pushes downward. Therefore, we need a new car. This one. As you can see, it has a little rear wing right here. This is going to help its grip on its tires so it can go around the turns with a faster speed without slipping. This is because right here is going to provide a downward force onto the car.
Good morning, Vietnam!
I think I died in an accident, cause this must be heaven. I gotta testify. Come up in the spot looking extra fly. For the day I die, I'ma touch the sky.